This is an introduction to spectroscopy. We do spectroscopy to identify an isolated unknown and to quantify the amount of compound in a solution. Today we'll demonstrate how to use a spectrophotometer, find out how it works using the Beer-Lambert law and absorbance. First we will turn on the spectrophotometer. You press the button on the back. On. Your spectrophotometer is made by Genesis and it will look like this as you turn it on. The first thing to do when measuring absorbance with a spectrophotometer is make a blank. The blank performs two functions. It allows us to zero the spectrophotometer for the given wavelength. It also allows us to subtract any unintended absorbance measurements of any component which we do not wish to measure. I adjusted the micropipette to 1000 microliters since I am using distilled water as my blank. If you are not using water as a blank, you need to put all of the reagents from the reaction in the protocol in the cuvette except for the substance whose absorbance you wish to measure. If you come to the spectrophotometer and the screen is unfamiliar, press escape until the screen becomes familiar. If the mode isn't in absorbance, you want to press the button under change mode until it shows absorbance. If the wavelength needs to be changed, you can press the button under set nanometer and manually change the number. Every time wavelength is changed, the blank needs to be remeasured. Once the blank is ready, place the cuvette into the spot prepared for the blank, marked by a B. When handling the cuvette, don't forget to only touch the ridge sides to prevent smudges. When placing it into spot B, orient it so the light will penetrate through the smooth sides of the cuvette. Once the cuvette is placed in the blank spot, you can zero the blank. This can be done by pressing the button below the words "Measure Blank." Once the blank is ready, you can insert the cuvettes containing differing concentrations of the substrate. Remember to handle the cuvettes on the ridge sides. Make sure you know which concentration is placed in which spot, which are numbered from 1 through 5. When closing the lid, make sure to measure the blank again. Press each numbered corresponding button to measure the respective dilution's absorbance. The absorbance will show on the screen. We made a large-scale model spectrophotometer to explain how one works. We will explain the components of the Beer-Lambert law with help from the model. This is a straight-on view of the spectrophotometer, and now I will explain the different parts. The first component is a light source, as modeled by these lasers of different wavelengths. A diffraction gradient, or monochromator, diffracts the light so only one wavelength passes through the chamber. This roll of tape symbolizes an optical system, which focuses the desired wavelength to pass through the sample chamber. A sample chamber holds a cuvette, which is modeled by this solid block. The light that passes through is measured by a photodiode. A recorder, in this case a computer, then displays the absorption of light by the photodiode. Just as our model shows, when a spectrophotometer is turned on, a sample's absorbance at a certain wavelength is measured. Beer and Lambert found that light absorption is mostly dependent on 4 factors: chromophore concentration, light path, absorption coefficient, and wavelength. These factors relate in the shown equation known as the Beer-Lambert equation or Beer's law. Absorbance is A. Absorbance measures the log of incident over transmitted light. It is the unknown which we are trying to measure. Chromophore concentration is C. As concentration of a chromophore increases, so does the absorbance. Path length is represented by L. The path length is the length of the cuvette that light travels through, usually 1 centimeter. The absorption coefficient is epsilon. Different compounds absorb light uniquely. The absorption coefficient shows the ability of a given compound to absorb light. And wavelength is lambda. Absorbance and absorbance coefficient are dependent on the wavelength of light used. The smooth side of the solid block represents a reagent blank, which allows light to pass through at a high rate. Turning the block to the rough side signifies a sample having its absorbance measured. Not as much light passes through to the photodiode when compared to the blank because it is being absorbed by the chromophore sample. The measured absorbance increases with sample concentration. We hope this has been a helpful introduction to spectroscopy. Thank you for listening.